Okay, now let's take a look at the time complexity analysis of this algorithm we just described and how to make it in general efficient. In particular, we're going to look at a randomized version of this algorithm. Okay, just to remind you, here is the algorithm we have. This is a recursive algorithm. We first do partition, and then depends on the rank we're looking for compared with the pivot, where the pivot is the order of the pivot. Okay, we have three possibilities. We either immediately return, or we recurse to in the left, or recurse in the right. Okay, so that's the algorithm. Okay, and when we're given the input at the top level, we call the QuickSelect over the entire array from 0 to n, looking for element k. Okay, all right. If we think about worst case time complexity, okay? So in general, again, let's use T of n to represent the worst case time complexity for the current, if the array you're looking at right now is of size n, okay? So how do we write out the worst case time complexity for this algorithm? Well, this take only constant time, okay? And this line, if it happens, also takes constant time. Okay, but here, whether we call this or this depends on whether the pivot order is bigger than k or not. Okay, but let's first figure out line by line what's the time it's needed. If we go to the left, okay, how much time do we need? Well, if we go to the left, we basically so at the beginning, we have s equal to 0, t equal to m, okay? So if we go to the left, we basically only recurse on the left portion whose size is only m. So if we go to the left, this is the time we need, okay? In fact, the size is m minus 1, okay? Or if we go to the right portion, then so right now, remember you have this array from 0 to m, and then with the pivot is here. We either go to the left or go to the right. If we go to the left, then we recurse on the left, and the worst case time complexity is the time running on input of size n minus 1. Or if we go to the right, we recurse here, and the time we needed is basically the time for this algorithm on an input size of n minus m. So that's what we have, okay? But how do I put them together, okay? In particular, I don't know which one I'm going to. Do I go to left or do I go to right? We don't know. But since we care about worst case time complexity, when you have if, then else, when you have different cases, you have to ask yourself, what is the worst case then? Okay, in other words, the time complexity will depend on which one is worse, which one is bigger, okay? Because you're preparing for the worst case. So for these two possibilities, you look for the worst case. And everything else is constant. Oh, sorry, I forgot to say, this is not constant. The partition is linear, sorry. So everything else take only linear time. Okay, so here's Cn, sorry about it, okay? So the trick here is that among these two choices, you go to the worst. You look at the maximum of them. So this is your worst case time complexity recurrence. Okay, questions? Okay, so this is what we have. But we look at this. This is not great. We don't like it because we don't know what is m, right? And so this recurrence is very different from all the other recurrence that we've seen before. This recurrence is not very friendly, okay? And we look at this and let's first just think about it. For different m, clearly, I'm going to get a different recurrence, right? So what would be the best case? For what value of m would this be the best? Well, intuitively, okay, what are we doing? So in general, let's just look at a few number of m, okay? If m equal to, say, m equal to 1, then this is t of 0, and this is t of n minus 1. In this case, then the bigger of these two clearly is t of n minus 1. So the time complexity is always an increasing function. So the bigger the variable is, then the bigger the time is, okay? So in this case, So if m equal to 1, then we have that t of n equal to t n minus 1 plus cm. Okay, intuitively, what is happening? Intuitively, after the partitioning, okay, your pivot is here. And we didn't really eliminate any numbers at all. We still have to recurse on a huge portion. So that's not great. Okay? Okay. What if m equal to n then? If m equal to n, then t of m minus 1 equal to t of n minus 1, and t of n minus m equal to t of 0. That means that my recurrence become t of n equal to which is the maximum of this two is still t of n minus 1. So in other words, if m equal to n, that means that after partition, the pivot is here. So again, I have to recurse on the left portion. I didn't eliminate anything. Okay, so both of these two cases, we can immediately see they are not great cases. Okay, because how can we make it faster? We make it faster if every time we can eliminate many numbers and only recurse on a small portion, right? So the question is that what is the smallest portion that you can recurse on? Okay, and it's not hard to convince ourselves that that happens when your pivot is in the middle. Okay, because when the pivot is in the middle, then no matter you go to left or you go to right, each of them only have size roughly n over 2. So it doesn't matter which side you go to. Whichever side you go to, you can always eliminate half. So you can always eliminate half of the numbers and only need to recurse on the only half of the original number. Okay, so and you can see that if you make m bigger or smaller, then because you always go to in the worst case, you have to go to the larger of the two, left and the right. Okay, so when m in the middle is the most balanced. Okay, so every time we find m in the middle and we remove half of the number, that's the best you can do in worst case. Okay, and this gives us a recurrence. If this happens every time, okay, if we're very lucky, then we get the following recurrence. And this recurrence, if I solve it, this equal to c times n over 2 plus, so this is simple. This is similar to some of the homework problem you did. This, if I expand it a few times, I get n over 4 plus c times n over 2 times cn, which is equal to t of n over 8 plus c times n over 4 plus n over 2 plus cm. And then the general pattern is that okay, and we stop when n over 2 to the k equal to 1. So basically, k equal to log m base 2. Okay, so we stop when that happens. We basically have here, which is cm 1 over, what I'm going to invert the order, cn. This is 1 plus here will be 1 over 2 plus 1 over 2 squared, all the way plus 1 over 2 to the k minus 1, okay, plus constant. The point being that this is a geometric series. It only adds up to a constant. So this is a constant, this is Cn, the whole thing as such give me linear time, okay? So if you will get very lucky, every time the pivot is in the middle, okay, then every time we can remove half of the problem and we only need to recurse on the remainder half of the number. And in this case, we just show that you can solve this recurrence give you time complexity, which is only linear, okay? So this is similar to the problem we've seen before, okay? All right, so this is the best case, let's take linear, okay? But if it's the worst case, as we said, in the worst case, intuitively, you couldn't eliminate much. If every time you only remove one number, you still have to recurse on n minus 1 number of size of the array. Okay, we send that to the 1m equal to 0, 1, or 1m equal to m. Okay, and for this one, if you solve it, then this equal to t m minus 2 plus c m minus 1 plus cm. If you expand it, and you can see that in general, after k times, you have c times m minus k plus 1 plus c times m minus k plus 2 plus c m minus 1 plus cm. Okay, so this stop 1 m minus k equal to, say, 0. That means k equal to m. That means that this gives us c. I basically have 1 plus 2 plus 3 all the way plus n plus this is constant, and this is arithmetic series that give me quadratic time. Okay, so as we see that in the worst case, when unlucky, okay, every time we can only eliminate one number, has to still recurs on a big portion, then in the end, this algorithm take a quadratic running time. Okay, so that's what we have. All right, so basically, so far what we see is that in the good case, the algorithm can be very efficient. If we cut it, if every time we can remove half of the number, then the algorithm is very fast because the size of the problem reduces very quickly. First it's n, then it's n over 2, then it's n over 4. So very soon you cut down the problem size to be so small, then you can just become constant, then you can just return. Okay, but in the worst case, each time can only remove one number, and then the algorithm is quadratic. Okay, so intuitively, by the way, this also means that the worst case time complexity is quadratic of the QuickSelect. Okay, all right, but then you ask, how can we make sure that, how can we have a strategy to make sure that we only have the good cases, so we don't have this bad case? Okay, so in fact, now intuitively, you don't have to every time remove exactly half of the numbers. Okay, as long as your pivot, okay, you have a good case, as long as your pivot somewhere lie in the middle range. Okay, then we call this a good split. Okay, well, let's say that suppose your pivot is here, and here is 1/3, and here is 2/3. Okay, then whichever side I'm going to, let's say I'm going to the bigger one, then I'm still removing a constant fraction of the number. Okay, it's not as good as removing half, but it's still pretty good. Okay, because you're still removing a constant fraction. Okay, and you cannot do this too many times intuitively, because I mean, if every time you remove a constant fraction, then you can only reduce the size by logarithmic number of times. Okay, log n number of times. So we call this a good split. So to know that for the good split, you don't have to really, the pivot doesn't have to, you don't have to pick the middle one. As long as you pick some pivot forcing within this middle range, you are good. Okay, so that's, and the bad split is otherwise. Okay, and if we always have this good split, again, namely, if we always remove a constant fraction of the, at least a constant fraction of the numbers, okay, at each recursive call, okay, then you can argue that the time complexity of the algorithm only takes linear time, same as when you remove half of the number, okay? And in fact, this can also be relaxed to that we don't have to have good split all the time. This can be relaxed to now that as long as you have one good split every few splits, okay, in other words, look at all the splits. If on average you have, this constant fraction of the time, you have good split, you are fine. You could have one good split, two bad splits, one good split, two bad splits, okay? That's okay. Still the time complex, asymptotic time complexity will give you linear, okay? So the question now becomes that, what can I do to make sure this happens? What can I do to make sure that on average, I have one good split every few splits, okay? And the idea to make sure that this happens, okay, is to use randomization, okay? In particular, let's say that we hope to choose a good split, namely, we want to choose a pivot whose order is basically in the middle. So I want to pick a pivot whose order will be between n/4 to 3n/4, okay? What does that mean? That means that after partition, okay, the left side of the right side each is going to be bigger than n/4, okay? And after no matter which side we go to, we will remove the other side. That means we remove, so this would imply that we can remove at least n/4 numbers after each split. Okay, if I can guarantee that my pivot falls somewhere in the middle, okay, then I can guarantee I would remove at least a quarter of the numbers each time. Okay, so how do I make sure that my pivot falls within this range, n/4? So that means that, let me just draw a different picture. That means that I want to make sure my pivot falls within the range n/4 and 3n/4. Okay, so I want to pick someone here with the rank here as the pivot. Okay, how do I guarantee that? Well, if I pick a random number in your input array as the pivot, okay, then what's the chance that the order of this pivot falls in within n/2 to 3n/4? It turned out to be 1/2. Why? Because if I pick a random number, okay, that means that any of the n number can be picked with probability 1/n, right? And then what's the probability you pick one number whose rank is between n/4 to 3n/4? Okay, that means that the number of the candidates of pivots that would satisfy this condition is 3n/4 minus n/4. Okay, you have this number of possible choices of the pivot. Okay, out of, in total, there are n number. Okay, so the probability by picking a random one, you force into this good candidates is basically the ratio of their number, which is 3m/4 minus 4m equal to n/2 divided by 2, which is 1/2. Okay, in other words, if you just pick a random number, okay, then with half chance, with probability 1/2, this random number, the order will be in the middle range. Okay, the middle range contains n/2 numbers. That's why the chance is 1/2. Okay, what this also means is that in expectation, every two splits, we will have a good split. Okay, because the good split happens with probability 1/2. Okay, so again, what did we say so far? We said that for me to guarantee that the QuickSelect algorithm work well, I want to pick a pivot better than just use always the last one, because then we can be unlucky. Okay, and I want to always pick a good pivot whose order is in the middle range. Okay, in the middle of the array. Okay, the reason is because if that happens, then I can, every time when the split happen, when we recurse on a sub problem, we can eliminate a constant fraction of the number. Okay, that would help us to reduce the size very fast intuitively. Okay, and to guarantee that this would happen most of the time, okay, we pick a random number as the pivot, okay, because when you do that, then with half chance, this will give you a good split. Okay, that means on average, okay, half of the time you get good splits. Okay, so that's the idea. And with this in mind, so here is the randomized version of the QuickSelect. Okay, and this this looks pretty much the same as before. The only difference here is here. in the random partition, instead of always use the last element as a pivot, now you pick one uniformly randomly in the current list as your pivot. Okay? Again, the reason is so you pick a random elements as a pivot. That's all the difference you make. Everything else is the same as before, but of course, for the recursive call, you have to recursively call the same randomized version. Namely, in the recursive call, you also, in the partition there, you also need to pick a random pivot. Okay? So this is the only difference. Okay? All right. And the code for this random partition, it's also pretty much the same as before. The only difference is this here. So before, we always use the last elements pivot, but now I pick a random one as my pivot. Okay. But for me to use the same code as before to proceed, I then put this pivot also in the last element so that I can still call the previous procedure to finish the partition operation. Okay, so this piece of code is the same as before. Okay, so all you need to do is that you first pick a random pivot, put in the last element in this current subarray, and then call the previous partition. That's it. Okay, so that's the only different modification you make. But the nice thing about it is that now, after we have this randomness inside, as we said, we know that in expectation, the good split happens with half probability, okay? And the bad split happens with also half probability. And every time a good split happens, the size of problem will be reduced by at least a quarter, okay? And so we only need to recurse on the 3/4 of the n of where n is the previous size, okay? So roughly to get given the intuition why this is sufficient to give us a good, why this is sufficient to give us a good expected running time, okay? So here, if you only focus on the good split, okay, what happens is that this is only the time incurred by the good split, a good recursive cost, okay? So the first time when we call it, we have the, we need to take Cn time, okay? And then we take one of the recursive call, but we know that it's a good split, which means that the recursive call is on a problem of size at most 3n/4, okay? That means that next time in this, after the good split, when we're in the recursive call, then the time to run the partition there, we only need C times 3. So this is a C times 3/4n, because I know that the problem size is at most this much. So the time is at most C times 3/4n. Okay, and the same holds later. And now if I have another good split, then the size again reduced to be only 3/4 squared times before. Okay, so every time the size become only 3/4 of the previous size. Okay, so the time to run partition on them is Cn for the first time you run partition, at most 3/4 Cn for the next time after good split you run the partition, and at most 3/4 squared times Cn for the next time you run partition after good split, and so on. Okay, so the total time, I don't even need to write when I stop, because when I take Cn out, I see that inside it's going to give me a geometric series, which means that this whole thing is constant. Okay, again, geometric series, remember 1 plus r squared is constant if r is smaller than 1, bigger than 0. Okay, so this is only constant. That's why the total time is only order of n for the good split. Okay, of course, we still have the bad split. Okay, but intuitively, the bad split happens only with probability 1/2, 1 minus p, which is also 1/2. Okay, so roughly, I'm going to draw a picture which is not really true. You can think that this is a good split, this is a bad split, good split, bad split, as we call the problem. Okay, now we know that all the good splits, the total cost, or let's make the good split green. Oops. So we know that the total cost of this green ones is only linear. Okay. Now, what are the costs of the bad ones? Well, you can chart each of the, so that should be a good one. And then we stop. After this one, we're done. Okay. You can intuitively, you can chart each of this bad one to the next good one. Sorry, to the previous good one. Okay, because I mean, right now this size cannot be bigger than the size for the from the previous split. Okay, so you can charge the cost here to the previous one. Okay, on average, each of them, since the bad one only happened with half probability, on average, each of them is only going to be charged to one of the good one before it. So in other words, the expected time for the bad one is smaller than the time for the good one. Okay, that means that the expected time in total equal to the expected time for the bad one plus the expected time for the good one, which is smaller than 2 times the time for the good one, which is, this is only linear, the whole thing is still linear. Okay, so that's the intuition. Okay, so essentially, what I'm saying is that even though that they're bad splits, okay, but the good ones, you can charge those bad ones, the total time spent on the bad one in expectation cannot be bigger than the total time spent on the good ones. Okay, depends on the probability P. In general, this is the bound we have. Okay, but since P equal to 1/2, then the total time, the expected cost that you're going to spend on the bad ones is bounded by the expected time you're spending on the good ones, which means that the total expectation is dominated by the good time, which is only linear. Okay, so that's the intuition. Okay, all right. This, of course, is not a precise argument, okay, just providing some intuition. This can be made more precise by using an inductive argument, which is a little bit involved, which we'll just skip in this class. Okay, all right. So what we just said is that the QuickSelect in worst case runs in quadratic running time. However, if you add randomness into it, then the expected running time of QuickSelect now becomes only linear, which means in practice, it actually, on average, it runs pretty well. Okay. In fact, it turned out that there is a select algorithm that runs in linear time in worst case. Okay, so the algorithm is a bit more involved. We're not going to cover that in this class, but the select can be done in linear time, worst case as well. Okay, but for this class, just know that we can select a specific order statistics from a list of unsorted number in linear expected time, which is the same as, which is the best possible, right? Because I mean, even to find the minimum or maximum takes linear time. Okay, all right. Let me just, in the end, let me just add another related topic, which is using the same idea. You can actually have another sorting algorithm, okay, called randomized QuickSort algorithm, okay, using very similar idea, which runs expected time is n log n, same as the merge sort, okay. Now, even though this is the expected running time, n log n, but in practice, QuickSort tend to be very efficient. Part of the reason because it's an in-place sorting algorithm, so it doesn't need so much memory. Okay, that's why in practice it's actually very popular, maybe more popular than merge sort. Okay, but what is the idea? So we talked about merge sort before. This is asymptotic speaking. The time complexity is optimal, is the best possible n log n under the so-called comparison-based models. Okay, but the problem with merge sort is that it is not in-place sorting. Because if you remember how the merge sort work, okay, so this is merge sort algorithm. Okay, in the merging step, okay, here we have to get a new array, merge the previous subarray and then merge them into a new array and return it. So you have to allocate new arrays. Okay, so it's not an in-place sorting algorithm. Okay, so I'm going to describe the QuickSort algorithm. Okay, this is in-place sorting. So the worst case is quadratic running time, but the expected running time is n log n. Okay. All right. So what's the idea? Well, again, let's look at the merge sort. What was the merge sort? Divide and conquer. So given this input array that we want to sort, we first divide it into 2 subarrays. Okay. Then for each subarray, we use this merge sort recursively to sort them. Okay, after that, each individual one becomes sorted. Okay, then we merge this 2 sorted subarray into a single sorted array using the merge procedure. Okay, so this is divide and conquer. Okay, now in this divide and conquer framework, the divide step is very easy. We just cut it in the middle, split it into 2. Okay, but then we have to do a little bit of work later at the merging step, because now we have 2 subarray, we have to merge them into a single sorted list. Okay, so this divide is simple, but we have to do some work here. Okay, what if we divide them more intelligently? In fact, how about we use the partition idea we just talked about to do the to split them? Okay, in particular, so here's the QuickSort. Instead of split in the middle, I'm going to run partition. I'm going to use a pivot to split the array into those smaller than pivot and bigger than pivot. Okay, so that's the first step. I'm going to run partition. Okay, next, what do I do? Then I'm going to recursively sort those smaller than pivot. And the pivot is here. And then I'm also going to recursively sort those that are bigger than pivot. So this is this step and this step. Okay? And after that, if all of this are sorted, I'm supposed to merge them into a single entire array sorted, right? But now notice, since P is already in the correct position after splitting, and here is everything smaller than P and everything bigger than P, and they're also sorted. I don't need to this merge now. I simply just, this give me already a sorted entire array, okay? In other words, if I use this idea, I don't need to do merging because after this step, this is already sorted. Okay, so that's it. So we compared to merge sort, I first put a little bit of work in dividing them. I use partition to help me. And then I split into those smaller than P and bigger than P. And I sort those smaller than P or bigger than P recursively. Now, after that is done, I get an entire array which is sorted. Okay, so this is the final entire algorithm. Okay, it's also very simple. Okay, also use divide and conquer idea. Okay, and well, unfortunately, the time complexity, we have the same issue as before, namely depends on, you see, this takes time, T of M, this takes time, T of N minus M. Okay, that means that the total time is actually T of M minus 1 plus T of N minus M plus Cm. Okay, the worst case is that, again, the split is not balanced. Then you get this recurrence, and that solves to quadratic running time. Okay, but intuitively, the best case is that you split in the middle. That's the same as then we get something which is the same as the merge sort recurrence. In that case, we get n log n running time. Okay, so again, just as it is, it's not good because we don't know. The worst case is bad. Okay, and now we want to make it have good expected running time, good average, okay? But since we cannot change the input, we have to add some randomness to the algorithm to make sure the split is on average always good, okay? And so compared to the previous algorithm, the only difference we make here is that we simply use the random partition. So instead of always choose a random pivot to do the split, to do the partitioning. That's it, okay? Everything else remains the same, okay? So with this one, the worst case is still quadratic, but by the best case is still n log n, but by a similar argument, intuitively, same as the random select, there are bad and good splits, but on average, we have constant, we have good split happens with probability half, okay? And the total time, expected running time is dominated by the good split. In the end, one can argue that the expected running time of this algorithm is still n log n, same as the worst case of merge sort. Okay, now compared to the merge sort in practice, this is even though the worst case time complex is worse, but because it's in-place sorting, okay, in practice, often people actually prefer this one. It often is actually faster. It needs a smaller constant, and also, most importantly, it needs much smaller memory. Okay, imagine that if your data set is huge, it's already 8 gigabytes. Okay, your memory is only say 8 gigabytes. You really don't want to allocate another memory, another array in the memory. Okay, so this memory become an important issue. Okay, all right, and that's all that I want to talk about today.